What we're going to do is apply Newton's laws to fluids in this chapter. Okay, so this is fluid mechanics. So let's start off by looking at the three states of matter that you're familiar with: gases, liquids, and solids. So again, in gases, the molecules are far apart and they're free to move about. So gases have neither definite volumes nor shapes. Gases take the shape of the container, and if you reduce the pressure on the gas, you can change its volume quite a bit. You cannot change the volume of a liquid much. Okay, you can increase the pressure on it, you can't change its volume. So liquids have definite volumes but not definite shapes. They take the shape of the container. Okay. Solids have definite shapes and definite volumes. So solids, you can't change their shape easily either. Okay. So what you'll see shortly is if the size of an atom, is about 10 to the minus 10 meters. Okay. In solids, the atoms are touching each other. In liquids, they are twice as far. Okay. And in gases, so if the atom is the size of your fist, okay, so in solids they're touching each other, they're that far apart. In liquid, and in gases they're about 10 times as far. Okay. So in a solid, the atoms are in fixed locations. So you can come back 10 years from now and that atom will still be there. In a liquid, if you tag a molecule, it's continuously moving. 3 seconds later, you don't know where it is. Okay. Similarly in a gas. Okay. So atoms in a solid are held in place. Atoms in a liquid are in close contact, but they can slide over one another. Okay. Forces between atoms strongly resist attempts to compress the atoms. So you can't compress them, you can't bring them any closer, okay? But they're not in fixed location. Okay? And atoms in a gas move about freely. All right, so what this chapter is about is applying Newton's laws to liquids. Okay? And we'll break it up into two parts. What we'll do is, first we'll study fluids at rest. We'll study the properties of fluids at rest, and then we'll study the properties of fluids in motion. Okay? So for instance, you'd be interested in situations like this. Let's say you're flying, and you could be flying in still air, or you can look at it this way. The air is moving over your wings, okay? And this motion, how this generates lift, okay? So we'll be studying principles of aerodynamics, okay? Fluids in motion. Okay. Okay, so the first quantity we'll define as density. Density is denoted by rho. That's the mass per unit volume. Okay. Now, I'll write this as mass. Volume is length to the power cubed. Okay. I'm just writing it to illustrate a point. So let's look at densities of some stuff. So density of a gas for air is about 1.3 kg per meter cube. Okay. So 1 meter cube is roughly this size. This much air has a mass of 1.29 kgs. That's about 2.5 pounds. Okay, so that much air weighs 2.5 pounds. 3 pounds. Look at the density of a liquid. It's 1,000 times greater. Okay, so this much air weighs 3 pounds. This much water weighs 3,000 pounds roughly. Okay, 1,000 kg, the weight of a small car. And look at this, the density of a solid. So when you go from gas to liquid, the density increases by a factor of 1,000. And when you go from a liquid to a solid, the density increases by a factor of another 10. Okay. So here we go. The density of a solid is 10 times that of a liquid. See, 2 cubed. So 2 cubed is 8, roughly 10. So if if the distance between atoms in a solid is that much, in a liquid it's twice as large. And since the density of air is 1,000 times less than that of a liquid, 1,000 times this would the length distance would increase by a factor of 10. 10 cube is 1,000. So if atoms are this far apart in a solid, they'll be this far apart in a liquid, and they'll be this far apart in a gas. Okay. So as the average distance between atoms increases, the density decreases. Okay. Okay. The next thing we'll define is pressure. Okay. So again, density is denoted by rho. So now we'll define pressure. So let me show you a little app first. All right, so here's an ideal gas, and you can see that these air molecules are bouncing off the walls, and the pressure they're exerting is about 20 atmospheres. Okay. So you guys know 1 atmosphere. So you'll see all these units. It's 10 to the power 5 pascals, but that is Newton per meter square. It's also about 14.5 or 15 psi. What does psi mean? Pounds per square inch. Okay. So what this means is that on every square inch, here is a square inch, air molecules bouncing off this square inch, like you see in this app, air molecules bouncing off. On every square inch, they're exerting a force of 15 pounds. Okay, so the air molecules bouncing off. So here's an amazing fact. Okay, this is 10 inches by 10 inches, 100 square inches. So the force that the air molecules bouncing off this surface are exerting 15 times 100, 1,500 pounds. Of course, why isn't it flying off? It's on that side also you have an equal and opposite pressure. Okay. Do you want to see the effect of this 1,500 pounds? All right, let me show you. Somebody have a pencil? By the way, on your example, sign. I can't read your signature.
I'm sorry.
All right, so how do I break this pencil?
Applying equal force.
So I need a fulcrum, and I apply a force here and a force here, and I can break it. Okay, why didn't it break?
There wasn't the same amount of force on the other side.
Yeah, I didn't have forces on either side. And the way you break this is, when you apply force like that, what happens is this bends, this becomes longer, and your actually pulling that stop side apart.
You got your pencil.
I'm sorry?
I said, say goodbye to your pencil.
It's all right. I have more.
Well, I mean, he's in full support of science.
It didn't break.
It didn't break. That's because,
You want another pencil?
You just disproved physics. You need a longer
You just
pencil.
I want the flatter pencil.
I took this class to learn how to break pencils.
You took this class before?
What's that?
Did you take this class before?
Yeah, that's why I write pen, so I can't break pencils.
This is my favorite demo, so I gotta break this pencil. Okay, this is better sheet of paper. Okay. Well, so the demonstration is as follows. If the sheet is flat, okay, so there's no air balancing the force there. Okay. So when I hit it, when this is lifted, air doesn't have enough time to get in there. So there are the 15 on the top. Because these pencils were like that, there's an air gap.
You need like a
Yeah.
thicker paper?
What's that?
You need a thicker paper?
I'm sorry?
Fits the pencil better.
You would need like a thicker paper that fits.
Yeah, or a flatter pencil. I normally bring rulers, flat rulers, and it works better. All right, so remember, these air molecules bouncing off exert pressure, and air molecules are light, and how can they exert 15 pounds per square inch? There's billions and billions of collisions happening. Okay, and that's how they exert pressure, and this happens in liquids as well. Okay, so you'll see that in a liquid, so you can see that in this liquid is exerting a pressure in all sides, and so it's liquid molecules bouncing off the walls that are exerting a pressure. Okay. Solid surfaces exert pressure as well, and that's also because solid molecules are also vibrating, and them bouncing off are exerting pressure. Okay. So pressure is force exerted by substance per unit area, and so units are Newton per meter squared. And that combination of unit is called a Pascal, after Mr. Pascal. All right, so for instance, if you go in a liquid, the pressure in a liquid increases with depth. Okay, so here's pressure is force divided by area. So force is the force exerted is pressure times area. Okay, so in a liquid, let's say this is the so this is the column of, this is air all the way to space, and this is a column of liquid. So why isn't this thing falling down? Because there is a force that's holding it up. Okay. This liquid is exerting a force, and that is equal to pressure times this area. Yeah. And as you go deeper, this column of water, liquid is increasing. So as you go deeper, the pressure must increase in this liquid. And that's what this is saying. So the pressure at a depth in a liquid, this is the atmospheric pressure, the pressure to balance the atmosphere. And this is the pressure, extra pressure needed to balance this column of liquid. Okay? So as you go in deeper in a liquid, pressure increases, okay, and it increases by that much. Okay? So there are consequences of this. Okay? Since the pressure increases with liquid and with depth, so when you build a dam, the wall, the deeper you go, has to be thicker because the pressure is greater, the force per unit area is greater, okay, and so you need the walls to be stronger. Here's another demonstration of pressure increasing with depth. Okay, so the speed at which this water comes out, it's the pressure here minus the pressure here. The pressure here is atmospheric pressure. So greater the pressure difference, greater the speed at which this liquid comes out. Okay. Yep.
Can you go back a slide to that one?
Yeah, just a second. So, and interestingly enough, the speed at which this liquid comes out, that's assuming if there's no viscosity, meaning it's frictionless. So for instance, if you put water in this jar and honey in this jar, will honey come out at the same speed? No, because honey, there's more friction. Okay, so this, what I'm going to state is for a frictionless liquid. Okay, the speed at which this liquid comes out, interestingly, is the same speed at which if you drop a rock to this height, the speed at which this rock will be going is the same speed at which this liquid is coming out. Did you guys understand that? So if I drop this rock from 3 feet, the speed at which the rock is going at 3 feet, and if that hole is at 3 feet depth, that's the speed at which the liquid is coming out. So greater the pressure difference, faster the liquid is coming out. All right.
One more. So the plus rho GH
Mhm.
is the rho, that's just the density of the liquid, right?
That's the density of the liquid.
And then gravity is G, and H is the height under the water?
Yep, height underwater. So the pressure at this point, see, P naught is the pressure at this point. That's the pressure needed to support this weight of air column. And then as you go deeper, you have to support more fluid. Okay? So that's the absolute pressure. That's the actual pressure. It turns out that if you go to a store to buy an instrument to measure pressure, what most instruments do is they won't measure this actual pressure. What they do is they measure this pressure. Okay, so we define something called a gauge pressure. The gauge pressure is the actual pressure minus the atmospheric pressure. Okay, because that's what most gauges measure.
So it's like delta pressure.
That's right. So when you measure the pressure in your car tires, when you go to a gas station and measure, that's the gauge pressure that's being measured. So the 32 psi, 30 psi that you're measuring, that's gauge pressure. So the actual pressure in your tires is 45 psi. 32 plus 50. Okay. 30 plus 50. So since the pressure increases, dam walls are thicker as you go to the bottom. Okay. So this is absolute pressure, which is actual pressure, and then we define gauge pressure. Just because most gauges, that's what they measure. They measure the actual pressure minus atmospheric pressure. So here's an illustration of that 15 pounds per square inch. Remember, this is 1,500 pounds. Okay, and you've seen this. So on your chest, this area is the chest area is maybe about 500 square inches. So 500 times, that's about 8,000 pounds crushing you. So why aren't you getting crushed?
Because there's the same pressure inside of me.
So you're breathing air inside your lungs, you have the same pressure. Okay. So this is 15 pounds per square inch. If you go to a depth of 33 feet underwater, 33 feet is roughly twice this height, that would be another 15 psi. So while you're walking around, there's 10,000 pounds crushing you. You go 33 feet underwater, now there's 20,000 pounds crushing you. So now what do you do? Huh?
Swim up.
So you have to breathe air at 2 atmospheres. Okay, so for every 33 feet, you have to breathe air at an additional atmosphere. Yeah. What happens is when you breathe the air at higher pressure, that air mixes in your blood. You popped a soda can? Okay, what happened? When you popped a soda can, suddenly you expose that air to atmospheric pressure, and now all the pressure the gas that was mixed at higher pressure bubbles up. Same thing happens in your blood. And that air would collect in your joints. Those are the bends. So when you go deep seas or when you go diving, you can't come up fast. You want to come up slowly. Yep.
Why do they breathe different mixtures of air?
Well, I mean, so at different pressures, the binding you want the oxygen to bind and then not just bind permanently. And you want to release that oxygen when you get to the and that's concentration dependent and all that. All right, so here's an illustration of that atmospheric pressure. Okay, so what this is this is an oil tanker, and what happens is after you empty it, it's steam cleaned. Okay, so somebody steam cleaned it and then forgot and closed the lid. At night, the temperature dropped, the steam condensed, and there was vacuum in there, and the atmosphere crushed it. All right, so you can think of the atmospheric pressure as the weight, so you have to apply a pressure to support this column of air, okay? And you have to apply a force to support this column of air, okay? So force is pressure times area, okay? So pressure is the force you have to apply per unit area. So if the area is 1 unit, 1 meter square, that's the force you have to apply to support the weight of this column of air all the way to space. Okay? And of course, if you go at a higher altitude, now you only have to support this column of air, so the pressure is lower there. Okay? So the pressure decreases with height. Okay? And it turns out that it decreases exponentially, and we'll show you that expression later. Okay. So a barometer is something that measures atmospheric pressure. Okay. So the idea is very simple. Okay. So you want to measure the weight of this column of air all the way to space. Okay. And what you're going to do is you're going to balance it with mercury. Okay, so this column they have the same area of cross section. This column of mercury, this weight is balancing this weight, and that's what a barometer does. Okay, so so to make a barometer, this is a trough containing mercury. What you do is you take a tube, fill it with mercury, put your thumb on it, and then invert it into this thing, into this straw. And so this, you have this column of mercury, this is perfect vacuum, okay? And so this column of mercury is balancing this column of air all the way to space with the same area of cross section. Okay? And it turns out that if the atmospheric pressure is normal, this column of mercury will be 776 centimeters high, which is that high. 760 millimeters. Okay? Now, if you made a barometer with water, this height would be 10 meters. It would be twice the height of this room. So that's why you don't, I guess, so that's why you want to make it with a liquid whose density is higher. Okay? And mercury has a density of 14 times that of water. Okay. All right, so we'll talk about pressure. Okay, so here's the slab of atmosphere. So here's this slab of air. Why isn't this falling down?
Pressure from both sides.
So if the pressure was equal from both sides, the weight of that thing should.
It'll be on the bottom of this.
So, okay. So, there.
Yeah.
Okay? That answered it. So the reason it's not falling down is that must mean that the pressure at the top is less than the pressure at the bottom. Okay? This difference in pressure is balancing the weight. Okay? So, so what this is the number of air molecules. This is the weight of each air molecule. mg is balanced pressure at the bottom minus pressure at the top times the area, okay, times this area. Okay, so that's the equation. Now, so what we'll do is initially we'll derive. So you guys know the ideal gas law. What is the ideal gas law? PV equal to nRT. Okay. Initially, what we'll do is we'll assume that the temperature of the atmosphere is constant, but it's not, but we'll assume that. Okay. Assuming the temperature is constant and starting off with this equation, what you can show is the pressure at height y is given by the ground pressure at the ground level, minus e to the power of minus mgy. What is mgy? M is the mass of a single atom. Okay, so this is the potential energy of a gas molecule divided by kT. K is the Boltzmann's constant, T is the temperature. Okay, so you see the pressure is decreasing exponentially. Now this is assuming that that the temperature remains constant, but as you go up for every kilometer, every 1,000 meters, the temperature decreases by about 6 degrees Celsius. Since the temperature decreases, the pressure must decrease. So the pressure actually decreases faster than exponential. Okay? All right, so the pressure decreases exponentially. Here, this gives you the number density. This is the number density at ground level. This is the number density of gas molecules at height y. Okay, number density is PV equal to nkt, n over v equal to p over kt. Okay, and this is the number density that they're talking about. Okay, so the number density is related to the pressure at height y. As this decreases, the pressure decreases. Okay? So what this expression is telling you is here they've put in the numbers for atmosphere and all that, and this is Y, and they've converted that, all the rest of the stuff, to meters. And it says 8,900 meters, 8,800 meters. Okay, so the number density at height Y is related to the ground number density like that times that. Anybody know what this is? That's the height of Mount Everest. So when you go on top of the Mount Everest at 8,800 meters, that becomes 1. 1 over E is, so the number density on top of Mount Everest is 37% that on ground level. So on top of Mount Everest, the pressure is 37% that on ground level. Yep. So climbing Mount Everest without oxygen, that's quite a feat. Yeah. Mr. Pascal discovered something interesting. Okay. Here's what he discovered. So here's an enclosed liquid. Okay. What is the pressure here right now? No, hang on this. Ignore that one. All right. So what is the pressure here right now? It's atmospheric pressure. The pressure here is atmospheric pressure as well. Okay. Now what we're going to do is we're going to apply a force here and increase the pressure here by, let's say, 0.1 atmospheres. Okay. What Mr. Pascal realized was if at any point in an enclosed fluid you increase the pressure by 10 psi, at every point in the liquid, the pressure increases by the same amount. Okay? So if you increase the pressure here by 10 psi, it'll increase by 10 psi at every point. So here we have interesting applications. So here the device, you increase the pressure here by F1 divided by A1. And the pressure increases by the same amount everywhere. So it increases by the same amount here. So F2 divided by A2 must equal that. All right, well, so let's solve for F2. F2 equal to A2 over A1 times F1. Okay, so let's say these guys are circular areas. Okay, so F2 is pi R2 square pi R1 square times F2 is R2 over R1 square times F1. All right, so if this is a small cylinder like that, okay, this is the master cylinder is small, and the slave cylinder is 10 times bigger. 10 square, 10 times bigger, 10 square is 100. The output force can be 100 times the input force.
Still have the same pressure.
Hmm?
And still have the same pressure.
And still have the same pressure. So this device is a force multiplier. Okay. It's a machine. The output force here was 100 times greater than the input force. Sounds like free lunch to me. And we all know there's no such thing as free lunch, especially. So what gives? Okay, turns out, here's the thing. What costs you energy? No free lunch meaning no free energy. Okay? So what costs you energy is work. Okay? So whatever work you put is what you get out. Okay? This is for a frictionless system. Okay? So input force force times input distance is output force times output distance. Okay? So when the output force increased by a factor of 100, the output distance decreased by a factor of 100. That's what happened. Yep.
That's what I was.
Okay. Okay. So that's, so if you push this 1 inch, if you push this 100 inches, that pushes only 1 inch. Okay. Okay, anyway, what does Pascal's principle say? That in an enclosed fluid, if at any point you increase the pressure by a certain amount, that pressure, that increase in pressure is transmitted undiminished everywhere in the liquid. That's Pascal's principle. Okay. All right, so again, if the output force is 100 times the input force, the output distance is 100th times the input distance. Okay. So the output work is the same as the input work. All right, so we are studying properties of liquids at rest. And here's the next important one, buoyant force. Okay, so let's look at this. You learned that pressure in the liquid increases with depth. So we've already applied this to air. So for instance, let's ask the question. So let's look at this block of liquid. Why isn't this block of liquid falling down? There must be a force. Well, gravity is acting on it. Gravity is acting on it. So why isn't that falling down? There must be a force, upward force in the liquid. And where is that upward force coming from? Because the pressure at the top is less than the pressure at the bottom. That's what's holding that liquid up. Okay? So the pressure at the top is smaller than the pressure at the bottom. So now instead of this liquid water block, let's put an object there. The same thing is true. The pressure on the liquid at the top is less than the pressure at the bottom. Okay, so as soon as you put an object in a liquid, there's an upward force due to the liquid on the object. So if you weigh this object in air versus in this liquid, in the liquid it should weigh less. Okay, and that's the buoyant force. Go ahead.
So does that mean that your buoyant force would be almost directly proportional to the volume of the...
It will be proportional to the volume. Mr. Archimedes told us exactly how big this buoyant force is. Yeah? And that's the Archimedes' principle. So Mr. Archimedes found out, so if you ask how large is this buoyant force, what Mr. Archimedes realized, when this object displaced this volume of the fluid, the buoyant force is equal to the weight of the fluid displaced. And there comes your volume comment. So if you displace 10 pounds of fluid, the buoyant force is 10 pounds. You displace 20 pounds of fluid, the buoyant force is 20 pounds. So if you have a 10,000 pound boat that needs to float, what does the boat need to do? Yeah. And then you invite two of your buddies to go on the boat, add another 400 pounds. The boat has to sink a little more, displace another 400 pounds. Okay? Mm-hmm.
So the bottom of the crew, like those big ships,
Mhm.
way more than have a bigger volume at the top.
No, so here's the, okay, so this much fluid is displaced, and the weight of that much water is equal to the weight of that boat.
So the weight of the bottom doesn't matter.
No. The weight at the bottom, it's for stability. You don't want the boat tipping. The keel is heavier at the bottom, so it doesn't tip. Yeah. Okay. that is like, okay, you've done a seesaw. Here's a child, and you put a heavy person here near the fulcrum. So the bottom is heavy, it's like this guy. So if you put another child, this will balance. All right, so Mr. Archimedes, what he figured out was the buoyant force was equal to the weight of the fluid that was displaced, okay? And so the buoyant force is equal to this is the volume of fluid displaced, density of fluid times gravity. That's equal to the weight of this fluid displaced. Okay. It turns out that our density, is almost equal to the density of water. So underwater, if you don't panic, you should stay steady. You should be weightless underwater. Okay. So for instance, if you want to lose weight, the best way to lose weight is the following. Let's say you weigh yourself, you stand on a scale, gravity acts on you, and so this has to exert a force equal to your weight, and this is your apparent weight.
Just weigh yourself in the pool.
What's that?
I said just weigh yourself in the pool.
Yeah, you weigh yourself in the pool. Gravity. Now there's a buoyant force which is equal to gravity, so Fn, the normal force, is almost zero. So you're weightless, and that's why astronauts train underwater for space flights and stuff like that. Okay. So your apparent weight is equal to the actual weight minus buoyant force. When an object floats, an object will float if the density of the object, yep. Can somebody, I'll post this recording. Oh man. It messes up the recording, right?
It makes the recording out of sync with with the audio.
Do you know what might be the cause? I've been trying to fix this problem, and I bought a new iPad too. Hmm?
Have you stopped the recording?
Um,
Have you stopped?
No, I'm not.
Maybe stopping the recording, right?
What?
Maybe stopping the recording.
Yeah, but then I have to break up into 2 files and post.
Just edit them together, like a real YouTuber.
Yeah.
I'll remember that. I was going to buy you pizza tomorrow, but that just went out the window.
No free lunch anyways.
No free lunch anyways. Definitely no free lunch tomorrow. All right, so when an object floats, an object will float if its density is less than the density of the fluid. Yeah. The density of an iceberg, icebergs are made of fresh water and it's ice, and when you freeze water, it expands, so its density decreases. So anyway, this is made out of fresh water floating in the ocean. Its density is about 89%. Okay, and here's the relationship. The density of the object divided by density of the fluid is the volume displaced. That means this is the volume underwater divided by the volume of the object. So 89% of an iceberg is underwater. Every ship captain knows that. The Titanic captain knew that as well. All right. Actually, now is a good time.